In the last video, we looked at graphing things like this, r equals the cosine of 4 theta, except in that video, all of those numbers there were odd. And in this video, I want to look at what happens if they're even. It seems like the answer should be pretty obvious, right? It's just going to give us 4 petals instead of 3 or 5. And it's a cosine thing, so it's going to hug the x-axis. But if my petals are evenly spaced, like they were in the other video, then it's going to have to hug all the axes. So it's a little uncertain what's going to happen here, but let's go ahead and take a look at it. But before we do that, remember that we're starting at 1, 0, because if theta is 0, and 4 theta is 0, and the cosine of 0 is 1. So we're still going to be starting here and moving into the first quadrant. So yep, that's pretty much what I was expecting it to do. Now, because that's the graph is now pointing me in this direction, just like before, I'm expecting to go now into quadrant 3. So let's see what happens next. Yeah, that's pretty much what I expected too. Now, with a 3-petaled rose, I went up then into quadrant 2, but that's not quite a steep enough. It's not pointing in that direction. It seems to be pointing sort of almost here, which seems to imply that maybe it's going to go up and hug this y-axis. Well, that kind of makes sense. If it's going to have 4 petals, then it's going to need to have at least 1 on each axis. So let's go ahead and do that. Yep, it does. It hugs the y-axis. I'm continuing to move in essentially a counterclockwise motion. I go 1 more. Now I'm pointing down into quadrant 4, so I'll go down into quadrant 4. And at this point, I've got 4 petals. Well, almost. It feels like this one should complete that circuit, but it's not going to happen, is it? So let's see what happens when I complete this half petal. See if I can get how close I can get it to that. Notice that I haven't even got all the way to pi yet. I need to get to pi to complete the cycle. That's what the other ones did. So this one must need to go all the way to pi too. But I'm most of the way there. So how am I going to get from here to here? If I could close this, then I would have 4 petals, but no, then I'd only have 3. It's a little confusing, isn't it? So let's keep going a little bit and see what happens. Looks like I'm going to get another petal out of it, but how am I going to close that 4th one? Well, let's keep going. I'm going to shoot into quadrant 2 and start another petal there. So I have a nice symmetrical graph, but it doesn't start and end at the same place. So what's going on here? Well, what's going on here is that we need to go all the way to 2 pi to see the complete graph. I'll talk about why we didn't do that in the previous graph in just a minute. If I change this to 2 pi, then we get some more room to work with. Now I'm only halfway to 2 pi. So what do you think is going to happen next? We ended up here. Probably I'm going to continue. It makes sense that I would continue and finish that petal at least. And then once I do, I'll be pointing in this direction and I'm off to make another one. And then another one. Let's find out. There's the rest of, oh, I've got A only going to pi. Well, so I'll change that to 2 pi. All right, how far did I get? There is 3, roughly 3.14, and then sure enough, it continues. There's another petal, and another one, and another one, and another one. And finally, I get to complete the cycle. What's going on is that the cosine has a period of 2 pi, not just pi. And so for these graphs, I need the full 2 pi in order to get the complete graph. Notice that when I do that, I end up with 8 petals, 1 on each of the 4 axes and 1 in between each of the 4 axes. Let's go ahead and animate this. Remember that we're starting at 1, 0 because the cosine of 0 is 1. The cosine of 4 theta gives me an 8-petaled rose. So why did the cosine of 3 theta only give me a 3-petaled rose? Also, the cosine of 4 theta required a full 2 pi to get the entire graph. The cosine of 3 theta only required pi. I wonder what would happen if I graph the cosine of 3 theta between 0 and 2 pi. Well, Desmos does have some limitations, so I've had to create a second version of the equation down here. This is a replication of what we did in the previous video, where we basically had r equals cosine of 3 theta, and the theta, the angle, went from 0 to a, and a went from 0 to pi. That means that I can animate it. So here's what we did in the previous video. This was the cosine of 3 theta. Now that's no surprise because we've already done that, right? But we stopped at pi. What happens if we start at pi and go to 2 pi? This graph will be red, so it'll look a little different. That's so you can distinguish it from the previous graph. Are you ready? It's the same graph. Make it a little bit bolder. It's the same graph as the previous graph. What's happening is that because of the cycles, the number of cycles, they're basically repeating, but they're not doing it by going around twice. They're doing it by using negative values. So when I have an angle that's bigger than pi, the sine of that angle is negative. So let me back up a little bit. Here I'm in quadrant 1, right here. That means that I have either an angle that's between 0 and pi over 2, and my to plot the point, let me see if I can get this just a little bit more kind of on a line. There we go. So now I have a point right here. So I either have an angle between 0 and pi, and then a positive radius, or I have an angle between pi and 3 pi over 2. Sorry, between 0 and pi over 2, and a positive radius. Or between pi and 3 pi over 2, I'm on one of these lines, and a negative radius. And that's actually what's happening here. So I have to go around twice to capture the entire graph, but the second half of the graph is simply tracing over the first part of the graph. And with odd repetitions, that's what happens, which is why technically you only need to graph to pi. With even repetitions, like 4, if I do the first half in blue and the second half in red, you get that from 0 to pi. Let me back it up and I'll reanimate it for you. You get this for 0 to pi. You can actually see it feels like it's finishing its first cycle, its first half. It finishes there at pi. And then this one I want to do that too first, very quickly. And then I'll animate this one. Now I'm going to be starting where the angle is pi and continuing. And that's the difference. So you're getting those 8 petals with the cosine of 4 theta because the graphs don't overlap in the same way. The cycles, there's a phase shift between the cycles. So you end up with twice as many loops, twice as many petals. Okay, I'm going to put this one back so that it goes all the way to 2 pi. And this to 2 pi as well. Finish the cycle. And the reason I want to do that is because now I want to compare that to the cosine of 6 pi, or 6 theta rather, the cosine of 8 theta, any other even number. The cosine of 4 theta gave me 8 petals. So think about how many petals you think the cosine of this cosine of 6 theta is going to give you. Are you ready? Starting counting here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Twice as many as the number 6. So if you have an even number here, you're going to get twice as many petals as that number. If you have an odd number here, you're going to have that many petals. The other thing to notice here is that this cosine graph hugs both the x and y axes. With an even number, that has to happen, at least with cosine. Remember what we said, though, about a sine graph as compared to a cosine graph? If you have a cosine graph in the xy coordinate system and you want to turn it into a sine graph, you have to shift it pi over 2 units to the right. So if I shift it in xy coordinates, that's the same as rotating it in r theta coordinates. So if I shift this, I think I'll graph it as a separate, do it as a separate graph. R equals sine of 4 theta, 6 theta, I guess I'll stick with that one. That's a circle because that's just the sine of 6. Theta sine of theta, sine of 6 theta. Now if I turn off the cosine graph, you can see the sine graph doesn't hug any axes because what was here has been rotated. In fact, it's been rotated pi over 6. It's been rotated pi over 12. You can see here, this is pi over 6. Let me turn off sine for a second. This is cosine, and I want to rotate it. Normally, I would rotate it pi over 2. That's the phase shift. That's the horizontal shift between sine and cosine. But the pi over 2, right, that shift is, that angle is a third of the size, or a sixth of the size in this case, because it's 6 theta, cosine of 6 theta. So 6 theta has to equal pi over 2. Therefore, theta has to equal pi over 12. So that means that instead of having a loop here, I'm going to have a loop here for my sine graph. Okay, let's turn everything off except for my sort of super graph here. And I'm going to change this now to an 8. I have 1, 2, 3, 4, 5, 6, 7, 8, just half the graph is 8. And then 1, 2, 3, 4, 5, 6, 7, 8 is the other half. So I have 16 petals in cosine of 8 theta. Change that to sine. This petal right here will be right here. Not quite as far as it was the last time, because now 8 theta has to equal pi over 2. So we're looking at pi over 16 for my starting point. Well, I'm not going to have time to do much more here. Let's just pick a larger, actually I want to do sine of 2 theta. Yep, sure enough, four leaf rows. What about 20 though? As I get bigger numbers, I get more petals, but they get skinnier. And that's understandable. I have to squeeze more into the same amount of space. So I hope you can see from this that that's what happens with an even number. I'll put it back to something a little bit more reasonable. Remember, sine of theta was just a circle. That's a 1-petal rose. Anyway, let's go with 4. That's an 8-petal rose. So that's going to do it for this video, because guess what? I'm out of time again. I do want to do one more that deals with a completely different kind of graph again, and that's lemniscates. So look for that in a separate video.